So for question 7, you're going to be dealing with an LLRB bucket hash set. So that's going to be the same where you have as a regular hash set where you have hash tables of buckets, except for the only difference is that each bucket corresponds to an LLRB instead of a linked list or a list that we're used to. The way that it resizes is that it doubles whenever it reaches a load factor of 2, but it'll never decrease. Your hash code is constant time, but we can't assume that there's a nice spread, which means that if you insert n items, all of them could manage to get into the first LLRB instead of spreading out to the rest. So you might have just one full LLRB and everything else being empty. But it could also be a nice spread too. We just can't assume that. So we're only dealing with a single call, so you don't have to worry about amortized or averaging, anything to that sort yet for part A. So keeping that in mind and that we're using theta notation, we'll start off with put. So for the best case, our best case is if everything managed to get into the LLRB, the first LLRB, except for the current item that we're putting. So if that happens, then we have an LLRB here that has a size of 0. So then when we put an item in there, there's only going to be one item in there, which means that your put will be constant time. But for worst case, we're going to assume the exact opposite. So instead of putting it into this 0 element LLRB, we're going to put it into this really full LLRB that has n elements in there already. That as well, we're going to look at the load factor. So we're allowed to resize if we exceed 2. So in the worst case, happens that we manage to get to that load factor of 2, we'll be resizing. And a resizing means that you're going to get all of the elements beforehand and replace them into this hash set that is now 2 times the size. But if we don't have a nicely spread out hash code, it could just hash into the same bucket again. So if it hashes into the 0th bucket, that just means that we're going to be inserting n elements, each taking at upper bounding of log n time per item. So if that happens, your worst case becomes n insertions, each taking about log n time. For contains key, we're going to be looking for if the key is inside the hash set or not. So best case, we're going to go back to the very small LLRB where it only has the one element that we're looking for. So if it hashes into this this bucket right here, the LLRB only has one element, so you can check this one element to see if it is the key or not. If it isn't, you're going to return false. But yeah, the runtime would be constant time because you only have to check one element. In the worst case, we're going to be checking the LLRB that has everything in it. So you don't have to insert an element in the contains key. So we're not going to get that n log n action going on. But we will have the log n because to just traverse down the LLRB. At the worst case, it's going to be that element all the way at the end. So that's going to be log n time. For remove, the best case, we'll be removing the small LLRB. It only has one element, so if it is the element that we're trying to remove, then we'll remove that and it'll become 0. And it's constant time because there's only one element in there. For remove of the worst case, you will have this LLRB. Since we don't have to decrease the size after removing an element, we don't have to worry about resizing. So we won't have to worry about this n log n anymore, but we do have to go all the way down the list in case, down the LLRB in case the element is all the way down there. So just like contains key, this will be log n. Cool. So for part B, you're going to assume everything the same except for the fact that under no condition will the buckets be increased. So if it's never increasing, it's never decreasing, you're going to have a fixed size amount of buckets. And you're never going to trigger the resize function. So best case would be the same thing if everything went in here except for the current call to put, where you managed to put it in this box, this bucket, then you're going to have a constant time best case, same as when you had it before, so it's going to look roughly similar. In your worst case, you don't have to do the resizing, so you won't have that inserting n element kind of thing going on, but you do have to worry about putting the element all the way at the bottom of an LLRB, which means that you might have log n. Yeah. For contains key, since contains key, and also if you look at contains key and remove, the actions that happen within these two methods don't pertain to the number of buckets ever being increased or ever being increased. So that doesn't change between part A and part B. So we can just copy over the runtimes. Cool. For part C, we're going to look at more of the averaging case, or the amortized runtime after putting Q calls. And that means you're going to have Q insertions, and then there are going to be Q elements. Ooh, I can't write for my life. Q elements, and then M buckets. And the cool thing about this one is now our hash code can spread nicely among the buckets. So on average, you'll have Q elements per bucket. So you're going to have Q over M elements in each bucket. So if we look at the first LLRB that has a resize when it's too large, and you're putting it there, the best case and the worst case alternate in the fact that worst case happens so that it does a lot of the work needed to insert elements, and then afterwards best case happens for a relatively long time before worst case has to come up again. So it's in the similar sense as a regular hash set, where even though there's a lot of work going on in one, it can be toppled over. So you will have the same kind of runtime, amortized runtime as you do with a regular hash set. So you're going to have an O of constant time. So it's the same as part C, but we're going to deal with the no resize hash set. So for this one, a worst case doesn't happen when you have to resize. It just moves from best case to worst case. Best case being when your bucket doesn't have a lot of items in it, and then moving to worst case where you have almost a full amount of items in it. So since it is moving from best case to worst case, we can upper bound it with everything being the worst case of log n. But keep in mind, we got to log n, assuming that our hash code wasn't evenly spread out, so that all of it went in here into the first one. But for this one, we can assume that the hash code spreads out evenly, so each of the buckets does not have an upper bound of log n, but rather it has an upper bound of Q over M, which we decided is beforehand is the average amount of items per bucket, because it spreads out nicely. So for part E, if it is significantly, this one is to tell if it's significantly worse, the same, or significantly better. And by significantly, we just mean like amortized wise, there's a difference. So if we, actually all of the answers can be correct if you can explain it correctly. So if we assume that we're starting with part A, where it's assuming that there is no nice hash code spread, we can think about a time where your hash code is really bad. So if your hash code is really bad and everything goes into the first element, we're essentially going to just deal with an LLRB in this case, and with the regular hash set, we're going to be dealing with some form of a list, right? So in inserting into an LLRB, each one will take log time to insert, but a list will take n time to insert. So a log n time is better than n time, so you're going to say that it's significantly better in the case that we're assuming that the hash code is bad and it manages to go into everything else. Assuming that the hash code is better, or is pretty good, and it has an even spread, you can assume that they're about the same because you have a load factor of 2. If you have a load factor of 2, that means on average, your hash set will only have 2 items. And if you think about how an LLRB is structured, ooh, I'm running out of space. An LLRB is structured. It has one node, and then it might have a node to the left or to the right. But since each one is on average 2, it looks like this, and that's roughly what a linked list or any kind of list will look like anyway. So it's going to have the same kind of runtime because there's only 2 elements. In the case that you are in the same case, so if you want to think about a case where it becomes significantly worse, it's going to be in the case that your hash code is still good, but when you're comparing the LLRB and you're comparing the list, the difference is that for an LLRB, you have a lot of overhead that's coming out of it. The fact that it needs to maintain, left is smaller and right is larger, and, the moving up and moving down of elements just to maintain how an LLRB is made. That could help out with how the performance, that could hurt the performance of an LLRB, whereas in a list, all you have to do is append to the bottom. So in that case, with all of that small overhead, it can be considered significantly worse, though I'd argue about the significantly portion. Continuing on to F. F is dealing with a red-black BST that was in the optional textbook, but all you need to know is that it was a BST that can help out roughly with what an LLRB does. So all this is asking, though, is if we should take an extension-based approach or a delegation approach. Extension-based is pretty self-explanatory in the fact that it extends using the extending keyword, the red-black BST, whereas the delegation will be a class, and some variable in it will have a red-black BST in it. So considering how we're using an LLRB in this bucket hash set, we might want to lean towards delegation simply because what we're doing in this whole scheme of things is having a hash table of LLRBs. So in that case, you're using them as instance variables instead of extending them. So an extending would only mean that you could use, like, in a sense, only one of the BSTs. So we're not going to use that because we need a lot of them. Also, they are instance variables. So that's why it's delegation.